I would like to talk about an experiment with water wave about time-varying medium, and I would like first to thank the two postdoc and the PhD students that did this, Samuel Hidalgo and Angelique Campagnello. So let me first recall what is a water wave. It is not a very nice wave, I would say. So I'm not hydrodynamician, and I must say that it's a very complex wave. It's neither transverse nor longitudinal, or both of them, if you want. We always think it's a surface wave, but in fact it goes into the volume, decreasing exponentially in the volume. And it's highly nonlinear, but in a way that we don't like when we do optics. You know, it's not a perturbation, it's really nonlinearities like turbulences and stuff like that that are coming in and that ruin the whole stuff. And when you look at the equation, it's a Navier-Stokes equation, which is nonlinear. But everything goes well. So the good idea, the good stuff is that it's so complex that people don't use it. While in fact, it's the only wave that we can see as waves. With this, we can play with these waves very easily. It's very cheap. You can see them by eye, so a little a normal camera would do the job. Okay, it's in the time of the lab, so a few seconds, so no problem. And you can do many things with this kind of waves. So you need just to do a few approximations. So Feynman used to say this is dry water, I think, at the end. So you do a linear approximation. You say, OK, low viscosity or no viscosity, which is completely different by the way from when we talk about optics. OK, within a few wavelengths, the water is already absorbed. You think about incompressibility. This is pretty OK. Irrotational flow, OK. And then at the end, you get some kind of equation that you know and that is nice and that you can play with. And for us, I mean, at least for me, this is all what we need. The second things that is important in water waves is the dispersion relation. So the dispersion relation in water waves, you have two kinds of waves. One is a gravity wave. So this means that the force that brings back the surface is gravity. So it's omega 2 is equal to gk. And another type of wave is capillary waves, which depends on the surface tension and the density of the liquid. For us, this will be neglected most of the time. And last but not least, you need to take into account the fact that there is a depth in the bath. And this adds this formula, the hyperbolic tangent to the formula. OK, now if we look at the few cases that are useful, the deep water, you don't have the tangent, the hyperbolic tangent. In shallow water, you have HK that comes in at the first order. And usually we go in the gravity kind of waves. So gravity waves are long wavelength waves that you find. So for small case, as you cross this typical wavelength, which is called the capillary wavelength, which depends on the capillary and of course on G. And in that case, you end up finding this kind of dispersion curve. And now, for the best, if you go in shallow water just for gravity waves, now it becomes non-dispersive. Now it's not anymore water, for sure. OK, so most of the time we will use this. OK, so why is it so useful to play with water wave for time-varying medium? Because it's very easy to change, in fact, the dispersion relation. You just change G. And because using simply the equivalence principle of Einstein, you do an acceleration of the bath. This is one way to do it, a very simple way. And suddenly you can get changes that would, when you talk to people that are doing optics, they would dream about these kind of changes. Delta n would be 1, 2, 3, or even 1 order of magnitude. No problem. You just have to shake the bass enough to get that. So it is also very nice because it is fast compared to the propagation of the wave, so that's no problem. If you do that, okay, that can be a drawback is the fact that it's in the whole container, so the whole container is pretty homogeneous. And the limitation is usually when you do an acceleration, you need to have an average that is 0. Okay, most of the time. So you can do the analogy, and we play with Nader 2 years ago, I think, about the analogy. And the analogy is that the permittivity in electromagnetism would be 1 over G, and the permeability would be 1 over H. So this is very easy to change, by the way, in optics also, and for us. This is much less easy to change. This would mean that you change the depth of the fluid while it's going on. So I don't know how to do that, so this we will not touch. Okay, so now this is the pendant of Nader's talk this morning. So he talked about temporal illusion. Instead of talking about temporal illusion, I will talk about gravity illusion, which is basically the same, but when we play with gravity. Okay, so here is. So this is for you, Nader. You talk about this morning, so I will talk about how to play with a Kapitza pendulum type of excitation. That will be my first part. So we will shake the bass with a high frequency compared to the waves we were looking at. And in the second part, I will talk about freezing and amplifying waves. This will be the second part. So Nader introduced that very well this morning and gave the generalization for secrets. So by modulating, for instance, the impedance of the circuit, then you can remain stable instead of diverging. This is, by the way, an engineering way to change the property of a system, as we will see. But it exists in mechanics, for instance. In mechanics, for instance, you can change the mechanical property of a system by shaking it. And this is really known in mechanics. Okay, because Nader showed a small example, I changed mine to be more impressive. Okay, I have no sounds. It's okay, so you can play with this. Okay, it's bigger than yours. Okay, because you went to all these this morning, so I sum up, and basically what we do is we are in the inverted position here. So for the pendulum, you have a -1 here, and then you modulate at high frequency. So big omega will be the high frequency, and small omega would be here, either the frequency of the pendulum or the frequency of the waves we are looking at. So by doing some Kapitza derivation, basically it means separating you have 2 time scale, a slow one and a fast one, and at the end what you end up with is you have a term that is an average in this part, or it can be more complex, as Nader showed this morning. But in this case, it's very simple. So you have this term that goes there. And when you look at when this term is bigger than the -1, then you find out that for critical velocity of excitation, which does not depend, by the way, on the frequency, it's not a resonance phenomena, you have this formula, which is proportional to the square root of GL. Okay. So that's the basic of a pendulum. What I like also is this way of looking at this, and you can play with this. Maybe I'm not going to do this, but if you have a thing like that, if you see here, you change the reference frame, and you go in the reference frame of the turning point here. So if you go in this frame, here you realize what's going on here. in this frame, what you have a force that is going up and a force that is going down. And basically, at each cycles, if you look at the projection here, the torque is not the same. You have the same force, but different angle. So at the end, what you do is at each high frequency period, you have an average torque that is not zero, and then you can measure, and that you must compensate a gravitational torque that tends to go to put it down. Okay, and with this vision, you can understand it. So there's a very nice YouTube channel by Steve Mould where he does the experiment, and you can do it at home. So you have this stick here, for instance, and if I move it like that, I will see that the stick is going in this direction, which is okay, I try. Okay, I try not to. Okay, okay. But you can play with this. So it's a nice way to feel it, to feel this. Okay, now let's go back to waves and to water waves. What we want to do is we want to do a Kapitza pendulum with water wave. Can we do that? Can we use this principle to maintain some waves, some water or some liquid upside down? So the liquid is characterized by its density, its surface tension, which we don't really care, and the frequency we are looking at. And what you must do here, you must prevent any little perturbation to increase. So if you look at this from a local point of view, I would say, if I close up this, what I found is this is an inverted pendulum. Okay, so if I take this part of the liquid, for instance, and this characteristic distance, what I have is this is the turning point, and basically this is proportional to L. Okay, so basically what I have is a mass and something that is proportional to L for a given L that I want to maintain upside down. The problem with water wave is you need to do this for all the L that are available. And to do this, so you need to do something like that for all the L. And fortunately, the L are limited by the container size. And so at the end, you can maintain this water upside down for a given width for the container, provided you excite it sufficiently. And all these modes will be maintained like that. So if I write another way to understand that is to go with in the, let's say, in the Fourier domain, in the cosine domain, then you take the waves, the dispersion, the relation, which is written here, very simple, and you look it, okay, that's a normal case when you're not upside down. Everything is stable, fortunately, when you have waves. And it's always, omega 2 is always positive. Now, let's put it upside down, and this is what you get. So what you get here is that you've got a negative omega square for some of the k, the lowest k, so the long wavelengths, and this is due to the fact that gravity is making this unstable. Here, what stabilizes the stuff is capillary waves. So here, for this, you don't care. You need just to stabilize this. And when you do the calculation with, oh, by the way, you all know this. This is what is called the Rayleigh-Taylor instability. So basically, if you put some water or some liquid, usually viscous liquid, because water will go pretty soon, will drop pretty easily, you have this unstable frequency, or K, spatial frequency, that you can observe. So this is, when you do paintings, for instance, on the ceiling, all the droplets you get is exactly this. It's the most stable K that you observe upside down. Okay, you all know this. The problem is with this, usually it must be viscous, otherwise all the water is going down. So you cannot do the experiment easily with a bulk of water upside down. You need first to put it upside down before you stabilize it. Okay, that's the first trick. Okay, I can tell you we play a lot in the lab trying to do that. Yes, you must be prepared to get wet when you do this kind of thing. And so, if you succeed, at least, this is again the Kapitza equation. Okay, you do the same trick, low and fast variables, and the low variables, what you get is this term that is the square of the velocity at high frequency. It does not depend again of the frequency. You can change A or omega, k square. That is stabilizing, and you see that as I increase the velocity, I stabilize more and more k until I can stabilize the container. Okay, so now how do I create some liquid upside down? Aha, that's for Nader. He doesn't know yet, but it's for him. One idea is, instead of trying to turn, this is experimental physics, I can tell you, we get wet very, very often trying to get this upside down. Another way is to try to push some air below the layer. So if you push some air below the layer, you will pull the layer up, and you will do this. And this is very funny. There is a strange phenomena. If you put a bubble into water that is shaken, then you've got a Kapitza phenomena on the bubble. So this is written for the bubble, for the mass of the bubble. Rho is for the water surrounding the bubble. And V is, okay, so that's the force that applies to the bubble. And V is the volume of the bubble. If you think that, for instance, the volume and the pressure on the bubble follows an isothermal law, you've got this law. And if you do the same trick as usual, saying, okay, it vibrates at high speed, and you've got two time scale, then you can write this equation. And writing this equation, you realize that you've got depth, which we call it dc here, that if you shake sufficiently, the droplet will sink. Okay, so you can.
Is it really 1906? Is it really 1906?
Yes. Okay, so you see, you can do the theory. So okay, so here is the line, for instance, for one shaking. The one is going up and the other is going down. You can do a table. We don't really care, but this is special for Nader. Look at that, your idea. This is a bubble that we change the excitation, so we can put it where we want. Okay, so you put more or. If we do this at 3 dimensions, it's not, okay, it's not a drop, but it's a bubble. But you can put your bubble wherever you want in the liquid. So if we add some shaking like that, or shaking like that, we can write with this bubble somewhere. So maybe we can do it. Okay, we need to buy 2 more shakers. Okay, now let's try to do it. So this is water, so it's more like glycerol, but it does work. Let's do it. So we have a syringe, we put the syringe, and we put some bubble at the bottom, and at the bottom, it should stay at the bottom because we shake it. And you see here, we are levitating a part of the liquid, so this is, I think, 6 centimeters over 4 centimeters, and this is levitating. Why? Because this part is stable, because you shake it enough so that it becomes stable. And what you can do is you can play with it and do 2. If you can 1, 2, you can do 2 levitating layers, okay, and that are stabilized by Kapitza effect, okay, if you shake enough. And okay, I don't know how to say that in English, the cherry on the cake, that's it, okay? The ice on the cake, exactly. Icing on the cake is that you can have even a resonance phenomena. So you see here it's shaken, but not at high amplitude. But here it's moving much faster. So you can play with it in order to maintain more liquid up or down. So you do the experiment, you measure the critical velocity. It can be small, it can be very big. And now what we want to do is we want to play with this. So I can show you now we have this. This is an old. Okay, we published this a long time ago. So again, by the way, the fact that the boat upside down is stabilized is due to Kapitza effect. So you can again say, okay, I take a 2 time scale and I do the stability of Archimedes force. And you have two dispersion, okay? So you can say, okay, I can play now with a two dispersion relation, and you try to do this, and it's a bit difficult because it's moving a lot, and you have a lot of perturbation, so it's not very useful to use this. And in addition to that, the problem that you have is, I'm lying to you, this is not water. It is, oh, by the way, you see a kind of ray here, which splits the two into two rolling apart. It's not water. Why? Because you all know that you have the problem of Faraday instability. So the parametric instability, which is resonant, will happen at half the frequency of the shaking. So this is Faraday instability. So if you take a liquid and you shake it, you've got at half the frequency of the shaking this. And fortunately, there is no threshold for this instability. But if you put more viscosity, then you have a threshold that is increasing. And you must do that. Otherwise, it's raining from the layer due to the Faraday instability. Okay? So this is, so you can say, okay, I will use Faraday instability to observe the dispersion. Unfortunately, usually this is pretty small, and you've got anti-symmetric modes that appears, and so they do not follow exactly the dispersion that you would like to measure. Okay, so this is a bit of a problem to measure this, but what we can do, at least, is we can do it in the upright position, the normal position, and oh yeah. Yeah, I mean, this is, okay. Basically, in this liquid, we shake at 100 hertz, 1 or 200 hertz. So this is a slowdown. But the camera is not a fast camera, it's just a normal camera. No simulation with me. I hope, let me think. Yeah, okay. Okay. That's Nader. So if I take this, in fact, I've got effective gravity that is appearing. I can write it as an effective gravity, which depends on the square of the velocity at high frequency. So this is the amplitude at high frequency, and this is the gravity. And typically, this is the kind of velocity that we can get with our shaker. Okay, maybe you can have more, but you have to pay more to get more. So typically 0.3 is okay. But if you look at that, so my student told me, you're on Jupiter here. So basically you can, so she called the project Jupiter. And you can have 2 or 3 times the gravity of the Earth. So let's do the experiment. So basically it's a shaker, and you put, for instance, some bath, and you want to look at the wavelengths. Oh, here you have a little problem. It's a container, so there are boundary conditions. And if you want to look at the dispersion, you will have a discrete dispersion. So what we do, we tilt it a little bit in order that the Faraday instability appears in one part and get increased here, so it has no boundary for this part. Okay, so that's it. It's going on here. You see it's moving, or it can move, but it also is modulated because of stroboscopic effect that we want to get in order to know the frequency. And when we do that and we compare to the theory, we get a pretty good agreement with the theory. Okay, so we've got this. So this is a way to change the wave at low frequency with using high frequency wave. And it is interesting, you can do this also with a 1D cavity, for instance. Yeah, okay. So what I find strange is that you see you have different modes with the same cavity here that are made by the same frequency, just changing the gravity system. And this can have applications. So if you look at, for instance, you have a system with vibration, so you have resonances at some part. Maybe what you can do is you excite the whole system at high frequency in order to change the K, not the frequency, but the K in this part in order to remove the resonance that you can get in this part. So this could be used in kind of mechanical application. Oh, I want to show you what you get with okay. Oh, in real life, I mean, this was real life from the top, okay, but now with an iPhone from the side, okay, we colored the liquid so that we can see the depth of the liquid, and here you see we are far above the Faraday threshold, so it's really nonlinear. It's not a sinusoidal system. You see, this is a hydrodynamical nonlinearity, otherwise it should increase exponentially. Okay. And, okay, so that's for the dynamical part. So you can change waves with other waves at high frequency. But as for the bubble, for instance, or for the pendulum, you can also change the property of equilibrium properties with this shaking. And it is known because you must, I couldn't find one, but if you take a beam that is a soft beam and you shake it with at high frequency, it will go up, meaning that you change, in fact, this elastic property and the property of the beam. So you can change the static properties by exciting it at high frequency. So how do you calculate that? You calculate that again with Navier-Stokes and the conservation of mass. You put some conditions that are dynamical condition and kinematic condition, that it's the atmosphere at the surface. And what you do is you do an additional hypothesis is that the velocity in the fluid is mainly the velocity of the shaking, okay? That is huge compared to the small velocity that can appear for the liquid to move around. And when you do that with the perturbative method, it takes a few lines, you get this, which is a bit strange, the 1/4 here, but believe me, this is the right formula. So this is a new equilibrium formula. So meaning that, in fact, you can change the liquid surface by shaking it in an inhomogeneous way, okay? Okay, again, for Nader, because you wanted it. You can shake it and turn it, okay? And as you can see here, it's not a point pendulum. There's two problems here. First, you can calculate if you can do that, and then you must calculate if the surface of the liquid is stable. So you need to do vibro equilibrium. By the way, that was discovered by Faraday, because Faraday was shaking some liquid and saw that the shape of the liquid was changing. So you see here, in fact, you can imagine that if all this liquid was moving like that, it will fall, of course. So there must be a gradient of velocity around this, and this gradient makes that the pressure, the velocity here is smaller than the velocity here, and that you can have a pressure that is not the same. And here, what you can see here is a Faraday instability that is coming in because you're shaking so much that at the top, it's doing Faraday instability. So here it's even worse. And what is also, I found it funny, is if you do the calculation, you find out that the velocity on the surface is changing with this equation, okay, depending on the height of the liquid. At first order, you've got this, okay? And if you do the calculation with a pendulum with a flat surface like that, you find out exactly that the pendulum is going to be at the same angle as the liquid. So all this is coherent and is fascinating, I think. And if you try to turn, you need to shake. There is a solution, so shaking it sufficiently, you can go and rotate the whole stuff. If you don't shake sufficiently, when you go to horizontal position or nearly horizontal position, then it falls. Okay, this is expected, I would say. You can do better, you can do walls, liquid walls. That's, I think, 6 centimeters. Okay, so what you see here is that the top here is moving a lot, is doing Faraday, is moving more than that in order to maintain this pressure. And here you have a slanted ocean, I would say, a wave, that is remaining like that. Okay, now let's try to play with this equilibrium to both, so equilibrium, vibro equilibrium and Faraday. Okay, so this is a long bass that is about 60 centimeter. And when you shake, it's moving more on the side than at the center. And so what's going on here is that the liquid is moving so that it compensates and it goes to the equilibrium. And you can calculate, by the way, with the shape, you can calculate the velocity of the liquid. So with this, you can have any shape of liquid that you want. And if you do this and you add Faraday instability, just now, so again, Faraday instability at low frequency. It's not the Faraday instability that comes from the high frequency. So here it's coming. Okay, these are coming, it will come all around. You see, here this is nonlinearity. Okay, very interesting. But okay, so you have this Faraday instability, and what you can observe at the end is that the wavelengths, of course, are not the same at the center and on the side, because it's vibrating more on the side. So here you are on Jupiter, and here you are on the Earth. Maybe. You see here, you just have to measure the Faraday, and when you do the calculation, this is what you find. You find the vibro equilibrium shape, and you find also, by measuring the wavelength, the velocity, and you end up finding that they fit very well in each other. Okay, so this means that you have both an action on the static system and properties and on the dynamical property on the wave. Okay. Now I'm going to talk about the next part. So, is gravity under control. So I put under in parentheses because our system worked 2 weeks ago only. So I will show you. We get wet with, I mean, you see it tinted in blue. So we get wet in blue, in fact. But I show you some first results. So the idea is, you remember this experiment where basically we do the instantaneous time error. So you blow a source at the center of a bass, and what you do, you shake with the bass, you give a jolt at the bass, and you have waves coming back here. And this is time reverse waves that are produced at the interface, at the time interface of our system. When you do the measurement, so this is not simulation, it's all a measurement. And here what you do when you do the jolt, you produce this wave, so it's broadband system. They're going in that direction, and you produce exactly the time reversed waves that are going back into the focusing point. And then, if you want to publish in a nice review, you need to do some more than a circle. So let's see with a complex structure, what you can do is you can time reverse a complex shape, like for instance, a smiley. Okay, that was the past few years ago. And then we had a talk with Nader. And this is the article that Nader showed this morning. And this is the non-Foster scenario, where you have waves propagating here at positive permittivity, and then suddenly you decide to go to negative permittivity. And here the waves are not propagating anymore. So instead of having the classical sinusoidal solution, a propagative solution, now you've got the exponential increasing solution that is frozen in this part. And then when you go back, what you've got here is, this is standing wave, of course, because what you have done, you have produced waves at some point, and these waves, they have no, why would they go in that direction and not in that direction? So you produce waves in both directions, and these waves produce interferences, and you've got standing waves. So here is a representation of waves coming back, okay, in the other direction. And then we discussed, and then I say, oh, but by the way, when we were doing this experiment, this is the gravity that, so the shaking that we use during this experiment, and as you can see, so here we do nothing, and suddenly we do boom, jolts down, but you see it's minus 20 G, okay, so it's negative. So it's negative, so basically it's a non-Foster. We should be in the negative part of exactly as in the electromagnetic wave. So the question was, okay, it was maybe the same experiment, but how? Because we didn't realize it. Okay, the problem you have when you do this experiment is, Okay, so if I do a graph of this, so you have a simple interface. So the more basic interface, you go in time from refractive index 1 to refractive index 2. What you get is waves that are transmitted, so the same amplitude of wave that is transmitted, but change frequency. And an additional wave if you, okay, properly if you change the impedance of the system. You have new waves that are coming up, one that is transmitted, goes along, and one that is reflected, okay? Unfortunately, we cannot stay in this state, because for us, this is gravity. I mean, this is adding acceleration, and with a vibrating shaker. So with a vibrating shaker, you must come back really quickly in the first refractive index, okay? So this is what we do, and this is what we get. We got the equivalent of a Fabry-Perot in time. And because we cannot maintain this, we cannot get this Foster effect because the two interfaces are very short. Basically, they are a kind of Dirac, and you cannot do anything. So the question after this discussion was, let's try to do the experiment, not the simulation. Okay, maybe it's a good idea, but you need to do that, something that is moving and maintain an acceleration, not a vibration, not a shaker. So this is the elevator, so I call it the gravitational machine or the elevator. Okay, so this is a 3.5 meters high stuff. I show you in a slow mode, not so slow, but okay. So this is a bath, and it goes up like that. For instance, this is that's 2 meters. So you've got a bath here, okay, with light. You have a shaker included to do some waves. You can also have a blower in this, and you have camera that shows what's going on the surface of this system. Okay, that was maybe a few months ago, but then we have to change the sailing, and then we have to have a lot of showers, and it was very difficult to get this work. But finally, 2 weeks ago, after some work, we find out that we could do some experiment, and this is the result that were analyzed last night. I mean. Okay, so this is the camera from the top. So maybe we can do better from the analyzing the filtering of the wave, but you will see. So the camera from the top, this is what, okay, you can do with this system whatever you like, provided it's minus 5 meters per second in velocity, which is quite a lot. When we move it, I can tell you in the lab, nobody moves. And you can do 5G, okay? Let's look at what we get. So what you can do is you can program any kind of trajectory. And what we did is we programmed a parabolic trajectory. So basically what's going on is that the bass is going up in a way that we try not to perturb too much. So you need to go up so the gravity is increasing, okay? Then we do a parabolic jump, and then we go slowly down. And when we do this again. Okay, let's look at, so you have a source that is down there, and that is emitting now. Okay, so you've got this wave that is arriving. And at some point, what you will see is, so that goes to 0.2 G for the parabolic jump. Okay, maybe you saw something here? Here we go. Okay, so you've got wave, we cannot see very well, but you have two waves that are coming down. I'll show you in a better view. Let's put it, let's zoom in the, okay, so this is a wave, and you see here suddenly, boom, it goes down. Waves are produced by the boundary, and then it goes down again. I mean, they produce backward waves. You see here, yeah, the backward waves. So meaning that, in fact, what you got, so we go to 0.2 G, so we are not in the Foster regime. So it should not create some waves. But at the junction of the parabolic jump and the other jump, in the side of the trajectory, you have some change of gravity, of acceleration. And this produces exactly what you have in a single interface. So what you get is this. You've got a first interface here. So this is when we enter the parabolic jump, first interface. Then second interface there, where you have, again, the production of waves. But you see here, this wave that is going through the whole bath is changing its speed, of course. At that time, it's changing its speed because gravity is in the parabolic jump. It's changing its speed. OK, so we are not very happy, but I can show you also from the side. So it's difficult to measure, but you can see it better. So that's a side camera for, so you see it's, this is a wave coming in. Ping, here you see there's something going on and a wave going back, so we can see it pretty well. And here the second, so we are in the parabolic jump here, and the one that is going down. The problem is if we want to be non-dispersive, which is basically not the case, as you saw, is that you need to have a shallow water. When you have shallow water in hydrodynamics, then you have a damping. So the wave is damped when it's going in, but there's supposed to be no dispersion. So, OK, that's the first experiment. It did not work, fortunately, because we expected it would not work at 0.2 G. Now, let's try it. So now we excite at a bit more than 0 G. So it should be a little bit unstable somewhere now. OK. Boom. So as you can see, when it becomes unstable, it's clearly making some stuff. And then it's kind of frozen, and then it produces waves and a backward wave. I agree that we cannot see it very well. Maybe a zoom. This wave here is propagating. Then it enters into the mode of 0G, and it's producing a wave. So now let's look at this. Here we clearly see the first wave going in, okay, propagating normally. And then in this part where there's no G, you see here it's a kind of standing wave that is appearing. So there's no more propagation. There is just increase. So when you measure it, it's about 4 to 5 times increase there. And when you stop the 0G, you have two counter-propagating waves that are emitted in both sides. So I would say this is the first time we observe this non-Foster kind of time reversal system. From the side. Oh, you'll see. From the side, it's pretty funny. Look at that. So the waves, it doesn't know it will have to do something. Okay, and here, look at that. So it stopped completely. Okay, it's increasing, and then when you stop this, it goes fast there and fast over there. Okay, and you have got also these waves that are appearing again. So to conclude this part, okay, we need to do a lot of experiments to measure the amplification depending on stuff. But to conclude, first I want to say that this is something we discussed with Nader. The main difference probably, one of the main differences is that G is 1 over the permittivity. So when you want to do non-Foster system in electromagnetism, you have a problem when you go to negative permittivity. You need to go to infinity for the phase speed. Okay, and it costs you to go there in energy. In our case, it's the opposite. The velocity goes to 0, and then it starts again. So we don't have this problem. And what it means also, and I think it's a bit strange, normally we expect that time reversal, like that, is made by fast change of in time of the permittivity. In this case, you can be as slow as you like. So you go slowly above the 0, you increase as much as you like, and then you go back, and then you got this. So this is a quasi-adiabatic change. The phase velocity goes to 0. Okay, question is, okay, in electromagnetism, you can measure the energy that you put in the system. In our case, I really don't know. what's going on. So how does the energy that you put in the elevator, like changing the gravity, how does it feed the system? I have no idea. So we need to investigate this properly. Another stuff that I would like to study, so maybe in the audience some people are aware of this this link with space-time metric. We always interpret the change in time in our simulation as a change of permittivity. But you could also say it's not the permittivity that is changing in an analogy to cosmology. You could say, in fact, it's the space-time that is changing. When you change velocity, in fact, you change space over time. And what you can do is you can say, in fact, let's say it's not a change of velocity, it's a change of the metric that is doing so. And in fact, there is a study about that. And this study is done by Schrödinger in 1939 and later by Parker in 1972. And it shows that in the increase, in the inflation of the universe, so the metric is increasing, what you do is you create some particles. You create some waves in the classical way, but particles in the quantum way. And this inflation will produce some waves, and waves that are entangled and that are going so in the two opposite sides, exactly like the waves that are going in the two opposite sides. So I think here, when we see that the time is like kind of stopped and that it goes to the imaginary part, it would be very interesting to have this approach in order to understand the results. To finish, I would like to thank the team, and especially Samuel and Angelique that did most of the experiment. And I'd like to thank you for listening. Thank you very much.